Okay, so we will try to solve this recurrence. So last time I fill in the first two steps and then ask you to continue, okay? Uh, so we will go through all of the steps to see what is the solution for this. And previously I said that is n log n, but how can we come to the solution like that? So before we continue, let me remind you a little bit about the meaning of this recurrence. Remember that the recurrence here comes from the merge source analysis. Okay, so let me show you what we have. Okay, so last time we designed the merge source in that we have if n is 1, then we are done, meaning that we return, right? Uh, because any array with one element is sorted, so we don't need to do anything. Otherwise, we recursively sort the left half and recursively sort the right half. And after that, we combine the results using the merge algorithm, right? So that said, Tn is an unknown, Tn here is an unknown function that will tell us the number of steps needed for merge sort of an array of n elements. Unless what we did with the insertion sort, we cannot count the number of steps for step number 2, right? Step number 1, we know, say it takes only one a constant number of steps or big O1. We know number 3 will take us big O(n) steps, or in other words, n steps. And then we don't know how many steps we can count for step number 2. So Tn is an unknown solution. So we only know that it will take Tn half times for sorting the left half, Tn half times to sort the right half, and then merge them, right? Actually, n plus 1, but n and n plus 1 are similar when n is big enough. So that's why we came up with the recurrence here. So Tn is an unknown function of n that will tell us the number of steps. And we have to be able to find out what is Tn, right? In other words, we want to find the actual solution of Tn in that we have no recurrence on the right-hand side. Okay, so that is what we did last time. So let's continue. Okay, let's continue. So last time we did a few things here. Okay, let me repeat the whole process so you know how to do it for the homework assignment. So the method I'm using here is the recurrence tree method that explained in the textbook. But next time on Thursday, I will also give you two other methods, and it's up to you to pick the right one you feel most comfortable with in solving a recurrence problem. Okay? But let's start with something we have in the textbook. So first, we want to know what is Tn. Okay? So we will replace Tn by the right-hand side. So that said, replace Tn by the extra cost and then Tn half. Plus Tn half, right? So here, is step by step. And one more step, we will replace this one by replacing n with n half. So here I will repeat this one. And then we have Tn half will be, okay, n half plus Tn divided by 2 divided by 2, right? So it's n half and then Tn divided by 2 divided by 2, Tn divided by 2 divided by 2, right? Similarly, on the right-hand side, we do the same thing. So we start with the extra cost n half, and then we have Tn divided by 2 square, and then Tn divided by 2 square. So this one is step by step. And since I have a limited amount of space here, what I will do on the whiteboard is that I will use only one tree and then using the substitution step by removing the notes, okay? But if you want to do it on paper, like say for the homework assignment, I ask you to show step by step, then you have to go from here to here to here, okay? So it's a little bit, cumbersome for repeating the tree. So that's why next time I will show you few other steps that will help us to avoid the repetition of drawing the subtree again and again, okay? But let's start with what we have in the textbook. Sometimes the solution in the textbook is not the best. So that's why professor like myself, we always want to find an easiest way so the student can learn the subject and follow the algorithm. Okay, now let's repeat this process. And then, as I mentioned before, I will try to erase and rewrite instead of repeating the process like this. So first, I will replace Tn by n, which is the extra cost, and then Tn half, then Tn half. And then I will replace this one with the right-hand side here in that n is replaced by n half, right? So I will have n half, and then Tn half divided by 2, that is 2 square, and then Tn half divided by 2, right? So similarly, I will replace this one by the right-hand side again here. So I have n half, and then here I have T n divided by 2, okay? And then T n divided by 2 divided by 2, right? So similarly, I will continue this process one more time. Then I have T n 2 power to the third, right? Etc. for the other ones as well. Okay, so continue. Okay, so let me repeat here for this row. Okay, and that is enough for us to see the pattern, right? So we want to see the pattern by repeating the process for a few rows, and then recognizing the pattern. So now, starting from Tn, now we count the extra cost, right? Eventually, this one will go to, okay, n divided by 2, divided by 2, divided by 2, and eventually it will come to the point when we have only one element. Okay, if we have one element, how many steps does it take? One step, because we see, okay, we check if n equal 1 return. So it means that it takes only one step, right? So eventually this one will go to T1, right? So that is what we have. Okay. Okay, so here we also have T1. Okay, every branches will go to T1, right? Okay. So now, when we so come to the case in that we have only one element, then the algorithm will terminate, right? And what is the cost? What is the total cost for sorting n elements using merge sort? We just add every extra cost we have here, right? So in other words, Tn will be the sum of every values we have on this recurrence tree. Okay, so Tn will be the sum of every values we have here. Okay, so how do we know the sum of every extra cost the algorithm performed? There are many different ways to add them up, but the easiest way to add them up is by adding the values on the tree row by row. Okay, so on the first row, what do we have? If we add every element on the first row, n, we have only one element, that is n, right? So we have n, one element, and the value is n. So we have n as the result. For second row, what do we have? How many elements we have on the second row? Remember that the first row has one element, meaning that we have an array of n elements. And now we break it into two halves, right? So the number of elements we have on this row will be 2, right? One big array divided by 2. Okay, so we have 2 elements, and every element on this row we have is n half, right? So n half, 2 times n half is also n. Now, the next row, we know that the first one has one element. We can write it as 2 power to the 0. Okay? Now, the second one, we double the number of nodes on the previous row. Here, we double the number of values on the previous row. This one is 2, meaning that 2 power to the 1. Now, we have 2 square is the number of nodes, right? Times with the value at each node. We know that the first one we have n, the second one we have n half, the third one we have n half mean 1 over 2 power to the 1, right? So here we have n divided by 2 square. Okay? So the number of nodes will be double every time, the value will be cut in half every time, right? But when we multiply them, we still have n. Okay? So similarly, the next one, you should have 2 power to the third, 2 times the number of nodes, and then this one, the size of the small half will be cut in half, right? So that is n divided by 2 power to the third is also n, right? Okay. Continuously, we have, yeah, this process cannot go on forever because n is the number of elements. Every time we cut it in half, it eventually comes down to 1. Actually come down to 0 or 1, but we can assume that n is an even number. Actually is a power of 2, so that we always have 1 as the last, say, step for most solves, right? How can we assume that n is a power of 2? It's very simple. If you have a list like this, 1, 3, 2, it has 3 elements, right? Easy, we just add one more dummy value at the beginning or dummy value at the end, either way. Instead of 0, we can have minus infinity, that's fine, right? So that's why if we don't have, say, an even number of elements, we can add dummy nodes so that from n, we always come down to 1 after dividing by half. Okay? So that's simple, right? So now, we want to know that how many levels this tree should have. Okay. So in other words, we want to know what is the height of this tree. What is the height of this tree? Okay. What is the height? So here we know that this one we call it level 0. Okay. Why level 0? Because you look at this one. We can say that, okay, this one is level 0. And level 1, that is fine. Okay. 1 or 0, again, starting when we count with 0 or 1. But here, I say that this one is level 0 because I look at 2 power to the 0. It makes me, it reminds me something so I can remember. Okay? So this one is level 1, level 2, until what is the level of this one? Okay. In other words, how many levels or height this tree should have? Okay, any idea? Okay, let me explain that to you so you know what is the height of this tree. So here, when you look at this, level 0, you have n, and then divides by 2, divides by 2, divides by 2, divides by 2 until we have 1, right? So for this one, what is 1? 1 will be using this pattern and divides by 2, divides by 2, etc. Right? Let's say I want to know, remember that here's level 0, level 1, level 2. So I want to know what is the level of the last row here is x. It's an unknown value that I have to find, right? So what is the relationship between x and n? N divided by 2 power to the x will be 1, right? Because here eventually it comes down to 1. So now, if we have this function, then what is x? Multiply this one up, you have 2 power to the x is n. Then what is x? Take logarithm. Take logarithm base 2 both sides. You have on the left is x, on the right is log 2 of n. In computer science, most of the time we have log 2. That's why when you see log n, it means log 2. Okay? So sometimes we just neglect the number 2. Okay? So that's why we say that it's log n. Okay, so x is log n, right? So that said, the height here is log n. In fact, it's plus 1, right? Because here you have 0, 1, 2 to log n. So that means that is log n plus 1 is the total height, right? But when n is big, log n plus 1 or log n are almost the same. So that's why we say that. But the height here is theta or big O log n in general, okay? Okay, so that said, the height of the tree here is log n, and here is the explanation for us to see why we have the height is log n. Yeah, because here T1 is T of, let me use a different color. T of n divided by 2 power to log n. Okay, so n divided by 2 power to the log n, right, is 1. Okay, from here is what we have. Okay, so that is what we have. So that said, you see the pattern, the first row, the second row, the third row. So when we add all of this one together, what do we have? How many elements we have on this row? How many elements we have on this row? 2 elements. Too much. Remember that here, when I have 1, I have 2 power to 0, right? And then I have 2 power to 1, where 1 is the level of this row. And we know that the level of this row is log n, right? From here, I have the level of this one. So the total number of nodes on this level is 2 power to the log 2 of n, right? And then what is the value? Times 1. Okay, so the total number of elements on this row follow the pattern. 2 power to the 0, 2 power to the 1, until 2 power to the log 2 of n. Okay, so what is 2 power to the log 2 of n? Okay, let me remind you a little bit about the logarithm. Okay, this one is one thing when we use to calculate the level. Now, logarithm is something we use a lot in analyzing the performance of an algorithm. So we have here log A of B equals C. What is it? If and only if log A of B is the value, if and only if A power to the C equal to B, right? A power to the C equal to B. So basically the logarithm is the inverse of the power function. So you learn this in discrete math, but let me remind you just a few important facts about the logarithm so we can use it for calculating what we have here. Okay, it's one thing. The second thing we want to know is that log 2 of 2 power to the n is n, right? So you will see that here you have 2 power to the n equal to 2 power to the n on the left-hand side here. That is good, right? Okay, so now the next thing we have is log of A times B is log A plus log B, right? Okay, so why do we know that? Because we take 2 power to the log A plus here is 2 power to the log A times 2 power to the log B, right? Okay, so that is what we have here, A times B. Okay, and one more thing that we want to remember is that log 2 of any base of A power to the B is B times log 2 of A. Okay? All right. Why do we have that? Because here we take 2 power this. Okay. So here, for example, if we have 2 power to this, then you have 2 power to the log 2 of A times B is similar to this, right? And this one you have is 2 power to the log 2 of A is A, right? And we have A power to the B. That is exactly what we have on the left-hand side here, okay? So that is what we have this formula. Okay, the last one we want to remember is this formula. 2 power to the log 2 of n is n, right? 2 power to the log 2 of n is n. Okay. Why do we have this? We take log 2 side. Then what we have? Okay. Log of 2 power this will be log 2 of n, bring it down, time log 2 of 2. Okay. And this one is 1. So this one is log 2 of n. Okay. So as I said, when we say log, it means log 2, okay, of the same base. So from here we have 2 power to the log 2 of n, that is n. And Jared Martin said n elements on the last row. Yeah, that's good, okay. So now we add row by row. Okay. And all of the values we have are n. So the sum of all of the rows will be n times what? How many rows? Log n. Right? More precisely, log n plus 1, because here it comes from 0 to log n, right? So it's n times log n. Okay, more precisely is plus 1. But when n is big enough, log n plus 1 is the same as log n. That is why we say that is theta of n log n. Okay, so that is what we have when we analyze the complexity of the merge sort. So starting from a recurrence here, we will try to go level by level and until we reach the base cases. And the base cases are the cases when the sub array has only one element. In that situation, again, we call it a base case, but base case means the algorithm does nothing, right? Because any array of size 1 is sorted. Okay, very good. So that is the way we analyze the complexity of this merge sorts. So any question you have? One thing I would suggest to you is that to go back and then look back at few important features of the log functions, and we need to use them a lot. That's why say try to remind yourself about this simple fact. Okay? You should learn about them in discrete math, but does not cost too much for reminding you. Okay. All right. So now, what's next? We have the recurrence with sonnet. Going back to the merge sort. Okay. Last time I asked you to design your own merge sort. In that, you have your own merge algorithm. Previously, I showed you that merging two sorted lists of size n divided by 2 will take us big O n steps, right? But why do we have that? Did someone design your own merging algorithm? So here's what we did in the class last time, right? We have two sorted lists. We want to merge them. Last time I showed you that we use 2 pointers, right? That point to the smallest elements of the two sorted sublists. And then we'll write down the smaller values, right? Etc. So an algorithm for doing that can be easily designed like this. So if we have two sublists or subarrays left and right, and we want to merge them into an array called A, in general, the left subarray can have P elements, and the right subarray can have Q elements. And of course, the combined list will have P plus Q, which is N elements, right? So we simply use 2 pointers I and J, and we initialize them with 1, and then keep writing the smaller values, right? By comparing the left, if the left value at I is less than or equal to the right value, at j, then we write down the left value, advance the I, right? Okay, etc. And finally, after one sublist is copied, we copied the other sublist, the rest of the other sublists, right? So analyzing the complexity of this algorithm is very similar to what we did for the insertion sort, counting the number of steps for each statement, okay? And you will see that we take only big O n steps for merging the two sorted array, the two sorted lists, okay? All right, now we just finished with solving this recurrence. Tn is 2t½ plus n with the base case of t1 is 1, right? So that said, we have the recurrence here with the base case, and we solve it here. So when we solve this one, something I have not mentioned, that is, when we analyze the algorithm like this, what is the best case, what is the worst case, and what is the average case? Starting with the best case first. For the merge source, what is the best case? Meaning, when does the algorithm work fastest? Any idea? Best case, for example, what will happen if the list is already sorted, or if the array is already sorted and we apply the merge sort? So what is Caleb said, and Jared Martin also said that n log n. Very good. Okay. If we have a sorted list, whether or not it's in the right order or whether or not it's the reverse order, merge sort does not care. They will have to apply the algorithm again and again, right? So that's it. For the merge sorts, best case, worst case, or average case, they are all the same, n log n. Okay? So that's it. Merge sorts is not the best because you can see that it does not take into account whether or not some part of the array is already sorted, right? So it will redo everything from the beginning. So that's why merge sorts may not be the best in the real world situation. So best case, worst case, average case, they are all the same. Okay, very good. So looks like you understand the concept very well. Okay, so that is for the merge sorts. Now the next thing we want to learn, and by the way, is there any question that you have regarding the merge sorts and the way we analyze the complexity? No? Okay, very good. So if you know how to solve this one using the recurrence tree like this, you should be able to answer all of the recurrences in question number 3 for the exercise 1. Okay, so exercise 1, now you can solve using the approach like this. Okay, question number 1 and question number 2, actually you can already solve using the knowledge you have learned up to this point. Yeah, so you are ready for solving all of the questions we have for the exercise number 1. So today I will explain a little bit more to you about searching. So you may need the idea of how to analyze the performance of a searching algorithm. So let me share with you the searching algorithm we have. Actually, I already posted the lecture note for searching on Moodle today. Okay, searching a list. So remember that we have two different search algorithms. One is the sequential search and one is the binary search. Okay, let's start with the simple first. So while I'm cleaning the board, just remind yourself about the linear search and the binary search. Okay, so let's start with one example. Okay, so we have, I just copy, few elements from the example I showed you on the share document. We have 16, 7, 10, 1, 5, 11, and 3, okay? Here is the list of elements we want to search. Sequential search does not require that the list has to be in any order, right? Unless the binary search in that the list has to be sorted first. But remember that if we have a list, we can sort the list first. It takes just only n log n steps, right? So it's very efficient. And then after that, we can search faster. That is the idea. And why sorting is important? Because sorting is the first step of the searching for any kind of information. Yeah. Again, here, you may think that sorting and searching are trivial, right? But if you look at Google, everybody have to use Google nowadays to search for the information, right? Of course, Google makes a lot of money from that, but it's another story, okay? So we just want to pay attention to what would be the usefulness of sorting and searching. So in order to have an efficient search engine like Google, they have to find a way to sort the information first. Of course, sorting the information here is not easy, right? That's why they came up with an algorithm they call PageRank for ranking their web pages, and then they can sort the web pages based upon the ranking. Yeah. That's it. That is the difference between Google search engine and the other search engine that nowadays most of them disappear. Okay, so that's why sorting is very important, because we have a lot of values. We sort them first, and then we just have to sort them once, and million users can start searching faster based upon the sorted list of values. Okay, so We will go into that a little bit later to see what will happen if we don't sort, and comparing between sorting a list and not sorting a list for a search engine. Okay, but starting with the sequential search first. Of course, sequential search nowadays, if we have to search the list once, sequential search, that's fine. But that is not the case in the real world. So that said, if we have a list, we want to search the list many times, like we have billion users, and then we should have billion search. Yeah. So if we want to have the target is 11, right? So the sequential search means that we compare the value at the first element. If they are the same, we found it. So meaning that we return the index of the elements we found, but here we don't find it, so we go to the next, go to the next, go to the next, go to the next until we found 11, right? So that's it. We compare. If they are the same, we are done. Not, we go to the next element, right? So that simple idea, we can design an algorithm, and I don't want to go into the details of designing this algorithm because it's so simple, right? So that's it. We just have a for loop. So for I from 1 to n, where n is the number of elements in the list, compare. If we found, we return the index of the found elements on the list. Otherwise, continue, right? So analyzing the complexity of this algorithm is simple, right? Correct list is easy as well. You can follow the lecture note that I provided for insertion sort to see if you can prove the correctness of this algorithm by yourself. Okay, it's very simple. Just use induction, and that's it, right? Similarly, we can count the number of steps we have, and then from there we can find out what is the best case, what is the worst case, and what is the average case. Okay. Starting with the best case, you can see that here you have the number of, operation we have for the first statement line is anywhere between 1 and n plus 1, right? The second line, then anywhere between 1 and n. Okay? Where j is the number of times the algorithm goes into the for loop. Okay? J can be anywhere between 1 and n. 1 means we found the elements at the first position. N means we found the elements at the last element or last position on the list, right? So what is the best case? 1, right? Big O 1. What is the worst case? Big O n, right? Actually, we have from here, if you add them, you have 2n's plus 2, right? N plus 1 plus n plus 1 is 2n plus 2. It's the same like big O n, right? Because when n is big, 2n or n are very similar, okay? Now, what is the average case? How can we calculate the average case for this situation? We have to know, okay, how many cases we have, and what is the smallest value, what is the biggest value, so we can add them and divide by the number of cases. So we have here, okay, the average case we have, the smallest number of cases is when we have only one step in order to find out the searching element at the first place, right? The second case is that we found it at the second position, and then the third position, and the last position. Every time we know the total number of steps, that is 2i plus 2, right? Where I is between 1 and n. So that's why you have the average case is the total number of steps for each cases and divided by number of cases, which is n. We have 1, and then we have 2, and then we have 3, and then we have 4, right? So add all of them up, then divide by the total number of possibilities, then we have the average case that is also big O n, right? So here we have the sum of I for I from 1 to n. We already know how to do that, right? It's the Gaussian summation. So it's an easy thing. All right, so a small calculation allows us to identify the average case. Okay. Worst case is big O n, best case big O 1, right? And then the average case also big O n. So easy for sequential search. Now, we want to analyze the binary search. Okay, the binary search, again, we know that if we want to perform the binary search, we have to sort the list first. Okay, so that said, we have 1, 3, 5, 7, 10, 11, 16. First, we sort the list, right? And now we can find 11. Okay. So finding 11, or let me change that one to 5, as I have in the note I shared with you. Okay. 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 In the shared document, I have actually the list from 1 to 16, right? But here, let's have another example in that we don't have 1 to 16, right? In fact, we have from the original list here, we sort that, and now we have 5, right? So that said, how can we find 5 on this list using the binary search? We all know about that, right? So that said, we first jump to the middle. Okay? We jump to the middle. Here's the middle. Jump to the middle and compare. 5 is less than the value at the middle place. So we search this one on the left. Okay, how to search this one on the left? We apply the same approach, meaning we jump to the middle and compare, right? 5 is bigger. Now we will find it on the right half, right? And now we found it, right? So that said, the algorithm is jumping to the middle and compare. If it's less than the value, search on the left. If it's bigger, search on the right. Okay. So what do we have as the algorithm? Remember that for the binary search, we have 2 different kinds of algorithm. One is the recursive design, and one is the top-down non-recursive design. Okay, so I'll show you both. And if you forgot that, then here we have. Okay, so on the left-hand side is the binary search, in that we use the top-down approach, meaning we simply use the loops in order to have the binary search. Yeah. Now, for the top-down algorithm, how can we analyze the performance of this algorithm, the one on the left, okay? On your left-hand side. So we know that we can count the number of steps for each statement line, okay? Do it by yourself, following the algorithm, following the method I used in the class before. Count the number of steps for each statement line, identifying the best case, worst case, and average case if it's possible. Yeah, of course, it's possible for this simple algorithm. Okay. Okay. I will not repeat that because we are focusing on solving recurrences here. So on the right-hand side, we have the recursive algorithm, meaning jump to the middle, compare if the value of the key is less than the value at the middle position, recursively search on the left. If it's bigger, recursively sort on the right. So that said, if Tn is the unknown is a function of n that represents the unknown number of steps needed for finding or searching for a key in the list of n elements, right? Then we have what? Comparing the value in the middle, first we calculate the index at the middle place, right? And then comparing. So it takes, say, 2 steps, but it means that, big O n, big O 1 step, right? So finding the values here, take the first index plus the second and the last index, add them and divide by 2. So it takes 2 steps, actually, 1 addition, 1 division, right? And then comparing that 1 step. So it means that it's 3 steps, right? So that set is 3 steps plus t and half. Okay? So here we have Tn is Tn divided by 2 plus 3. Well, plus 3 is a constant number of steps. So in general, we replace this one by big O 1 or simply 1 to make our calculation easier. Okay. The result will be the same, but if we write 3, the calculation will become more complicated, unnecessarily and more complicated. That's why most of the time we replace it by 1. If it's a constant value, we replace it by 1, right? Okay, so that is what we have for the recursive algorithm for binary search. All right, and now we want to solve this recurrence to see what is Tn. Solving this recurrence means that we want to find out what is Tn in terms of n without the t on the right-hand side. Yeah, so this one, we want to know what is it. For example, n, 2n, or n log n, or anything, right? So we want to find out what we have. Okay, before we come to writing down the solution, again, using the recurrence tree, let me talk a little bit about how can we compare between the simple or sequential search and the binary search. The idea is as follows. We have a list of elements. Okay. In general, if we have a list, we can have billion search, right? As nowadays we have for the internet, billion of users will try to use Google for searching for something. Okay, so that said, if we have 1 billion search, and every time if we use the sequential search, it will take n step, right? So meaning that it will take 1 billion times n, right? Now, if we sort this list, then it just takes us big O log n times n, right? Steps for sorting. We sort it only once. So that said, the cost is n log n for sorting. And now, if we have the searching here, okay, and assume that after we analyze this one, it takes us only log 2 of n or log n steps for searching. Then here we have 1 billion, and then we have just log n is the cost for 1 billion person searching for something, right? So if n has 1 billion elements, right, then 1 billion times log n will be much smaller than 1 billion times 1 billion. Okay? All right, so that said, if we sort, it takes us only n log n step. Okay, so let me have n is 1 billion also. Okay? If we have n is 1 billion, okay, so this one is more or less 1000 times 3, right? And then if we take log 2 sides, log 2 of n is here, 10 power to the third is 1000, is close to 1024, right? So here we have 3 times log 2 of 10 power to the third is 2 power to the 10. Okay? 2 power to the 10 is 1024, right? Okay, so that said here we have 10. Log 2 of n is 30, roughly, yeah, because this one is 1024 instead of 1000. So that said, here, if we have the sequential search, this one will take 10 power to the 18, right? Okay, so that is trillion. And this one, n is 1 billion, and this one is 30. So this one will cost 30 billion. Okay, and this one will take 30 again, right? Okay, so that set is time 60 billion instead of trillion, right? So this one is million times slower if we simply sort the array before and let, say, billion of person search the list. And that is what we are learning in this class. You are learning some simple algorithm like sorting, searching. But the question is, how can we make use of those algorithms to speed up something for the real life? For example, search engine for the internet, right? So we sort first and then we search after we sort it. Okay, so that is some motivation for why we are learning some basic algorithm like sorting and searching here. Okay, now let me go very quick to solving this recurrence. Okay. Again, I will use the recurrence tree in the textbook. So first we have here Tn is Tn half plus 1. So we have Tn, right? So I will replace Tn by the right-hand side. So that said, I have 1, and then the extra is the extra cost plus Tn half, right? Replace Tn half again by 1, and then Tn divided by 2 squared, right? And etc. We will go to T1, which is T of n divided by 2 power to the x. What is x? T1 costs us 1 step, right? So we need to know what is the height of this tree, and this tree has only 1 branch, right? Okay, so what is the height? Let me close this one so I can see your response. Okay, John Juban, you said log n. Okay, very good. Okay. Here you have n divided by 2 for the log n is answer n. So this one, x is log n, right? More precisely, log 2 of n, right? So we add them every level. It's always 1, right? So what is the sum? Sum of 1 for I from 0 to log n. What is it? You add 1 log n plus 1 time, right? So that is log 2 of n. More precisely, log 2 of n plus 1. But we know that when n is big, log 2 of n plus 1 is similar or almost the same as log n, right? So that's why we have Tn is log 2 of n, and it's the solution, right? It's the solution because it's a function of n, and it does not involve the t again on the right-hand side, okay? So you can see from here that it's a little bit different with what we did for the merge source, but you see it's very similar, right? By counting the number of extra steps, finding the patterns, see what is the height of the tree, right? The height of the tree is decided by seeing what do we have for what. It's n divided by something, right? And that is log 2 is the something we need to find. Okay, so it's pretty straightforward. We will try to have, I think up to this point, you are good for solving the problems for the exercise number 1. But next time, I will have more hands-on exercises for you for solving more complicated recurrences. So you will feel more comfortable with that. Okay, any question? If not, then I will mention a little bit about the programming contest training. Okay, so last time I received feedbacks from students who want to be trained for Southeastern Programming Contest team. So roughly speaking, around October, November, we will have the programming contest. Is either for South Central USA or is for North American universities. So we need to start training. So basically, I will post the training questions, and after we finish the homework exercise number one, then I will give you about 1 week to work with the programming contest problems, and then we'll go through the solutions with you so you can know how to solve how to design the algorithm for solving the training problems. Okay. So one thing I want to mention here is that I will have the training in the same format like we have at the programming contests. So I have a server for say handling the programming contest, and I will use it to train you as well. So here is what I have. Okay. All right, so I have a place, a server called train.celu.edu/domchurch, right? And now, once you go there, by the way, it's only available when you are within the network of Southeastern. So if you are not at Southeastern, then you have to go through the remote access, right? You go to desktop.southeastern.edu, and then from there you can go to this server. And we don't want to deal with the security issue, so that's why it's always available when you access through Southeastern. And here is the QR code. If you are at Southeastern, scan it, and it will tell you where you have. Okay. Once you are here, you can register an account. I let you open your account, and usually I will remove the account by the end of the semester. So for the next semesters, the new students will be able to use. So we have here the problems, the first 3 problems, focusing on searching and sorting. So for example, when you see problem 1, you can click at that, and it will show you the problem, right? How you can solve the problem with sample input and sample output. Okay. If you took the 280 CMPS 280 with me, then you already know the format we are working here. But for training for the programming contest team, it will be more challenging. So that's why we will work together, and we'll be able to help you to solve as much as possible. Okay, so when you log in, the first time you need to register, right? So after you register your account, then you can start working. As I said, this one is a heads up. I will really start working with you on this after you submitted the homework assignment number 1. Okay. That's it for today. And if you have any question about the homework, don't hesitate to ask. Okay. All right. So if you don't have any question, then Take care and bye bye.